I'm also going to record this for your purposes. Okay. Can you still hear me?
Yes.
Okay, so I have two screens here. So if you have a question, you could feel free to write a question in the chat room, or you can get on your mic and go ahead and ask me a question. All right, so the purpose of this workshop is to give you the background of a type of mass spectrometry, which I believe every one of you are familiar with the concept of mass spectrometry, which is essentially measuring the mass of different chemical species. And so what I'm going to orient you on is the mass spectrometry that has to do with MALDI time of flight. And so the word MALDI, what it stands for is matrix-assisted laser desorption ionization. So I'm going to define to you what does that really mean, because this is a technique that actually depends on the presence of a matrix of something else in order for you to be able to see the sample of interest. And so I'm going to gear you on the application of this particular technique with the instrumentation AB-SciX 4800 MALDI TOF. When you enter into the Molecular Science Research Center into the proteomics area, you will see that there's actually another MALDI TOF located right next to this instrument. And so I'm still use this particular instrument because I believe it's quite user-friendly for a number of different applications. The other instrument is available for you to be trained on. I'm not the one who's an expert on the use of that particular instrument. But nonetheless, all the concepts that you will be learning today, you can easily apply to either of the instruments. All right, so let's get a context of what exactly is going on within this instrument. So what you're going to have is a mixture of your sample of interest with a matrix. And we're going to define in a bit what exactly you have to consider as far as the choice of matrix, because you have to be very familiar with the samples that you're collecting. This is the reason why I've been communicating with the REU peer climb students to let me know what sample they're going to have and to be very particular about the prep of the samples. Because this is not a technique, like many techniques, you can't just go into it and start collecting things. You actually have to do a lot of brain work before in order to maximize the success of your experiment, but also to minimize the time that you need to dedicate to data collection and analysis. Right? So what you're going to have is essentially the mixture of your sample and your matrix. And what's going to happen is that it's going to transform into the solid form into an ion. And then what occurs then is that in this ion form, you're going to have the division of your different species based on their size. And there's going to be a mass sorting that occurs that's essentially going to involve your ions flying through a tube, being filtered based on their mass size, and then hitting a detector. And essentially what you're going to see is an output that looks like this, where you have a spectrum, a mass spectrum, that is essentially relative abundance versus the different species. And you're going to see this, the different species in terms of mass by charge. And so in terms of how we represent it is by M by Z. And then depending on the type of data that you're collecting or the type of experiment that you're performing, you may need to do additional processing of this data and subject it to a database in order to analyze your sample. What you're going to see tomorrow is the use of the instrument to be able to detect some simple samples, and you don't have to do much processing at all. So when you interact with the actual plate in which you're going to place your sample, what you're going to see are many little wells, and depending on the plate type, you may see as many as 96 wells or 384 wells. And so each well can hold an individual sample. So you can see how efficient this technique is. And actually it's going to be really small, these wells. So this is just a visual of a zoom in of a well from the side of it, and where you're going to have essentially a crystallized form of your sample and your matrix. Because essentially what this technique is that you're crystallizing your sample embedded into this matrix out of your solvent. And then that is what's going to get ionized, and you're going to be able to analyze it. And so the matrix is what's going to help to ionize your sample. So essentially what we're seeing is the following. A laser is going to provide a source of voltage, a source of energy in order to facilitate the ionization process. So you're going to have the formation of your matrix into ions, and then these ions are going to be transferred to your sample of interest, forming ions. For instance, you may have a simple transfer of a proton. Proton provides for a positive charge, and that will allow for you to see your sample in the positive ion mode. So the very important thing to note is that this is a technique that's going to see ions. So you can collect data in either positive mode or negative mode. And that's going to depend on the sample that you had, which mode you think you would prefer to collect in. All right, so let's talk a bit about this ionization process. So again, as I mentioned to you, you have that mixture of your matrix and your sample, and you're going to have a laser that's going to provide this source of energy. So you have this voltage that's applied. That is essentially going to then release the ions from the source, and then is going to be able to move from the source into the flight tube. And so this is essentially what's going to happen. And is the reason why this is called MALDI TOF. So let's talk about the first TOF. So there's a reason why we repeat the phrase TOF. Essentially, what that is time of flight, because what you're having is a movement of your ions through this flight tube. The smaller the ion is, the faster it's going to move through the tube. The bigger the ion is, the slower it's going to move through the tube. And then there will be a detector at the end that's going to be able to detect these different ions, and is going to register the output of data, again, as abundance versus mass by charge. So there are a number of important factors we must consider when we're working with this type of mass spectrometer. And so one of those is the mass accuracy. So what is the mass assignment of a peak? How accurate is the mass measurement? The resolution, how sharply defined, focused are the peaks? How well separated are the peaks from each other? And we're going to see that depending on the mode of collection, the resolution can vary significantly. And finally, the sensitivity. How small an amount can be detected and analyzed? So one of the beautiful things about mass spectrometry is that it is a very sensitive type of technique across the different types of techniques, instruments. But it does depend on what instrument, how accurate the mass is going to be. And I will tell you that MALDI TOF is not a particularly high mass accuracy. There are other instruments that are much better for that. But MALDI really is quite beneficial because of how quickly you can access the data and how quickly you can assess a lot of data. And when you're working with small samples, you really have the advantage of excellent resolution. All right. So as I already mentioned to you, one of the things about MALDI TOF is that it's not a high mass accuracy. Okay, and so this accuracy will depend on molecular size. So it's better when you're working with small molecules and gets progressively worse the bigger the molecules are. So when we talk about, with this particular instrument, samples, we're going to divide them into two categories. Those that we call small molecules and those that we're going to call big molecules. And what's going to be the deciding factor of dividing these two? Well, it's going to be this mass cutoff, where anything less than 10 kilodalton will be considered small. So that consists of peptides on the smaller end, molecules, organic molecules that some of you are working with, perhaps some of the metal compounds that people are working with. And then big molecule would be anything that is greater than 10 kilodalton. So what would fall in line with something that's a big molecule? Well, in this context, bigger sized peptides, proteins for sure. All right, so you will see that we will use different modes depending on whether we're collecting things that are small molecules or whether we're collecting things that are big molecules. All right, so the resolution. So here, I already jumped the gun a bit by saying that the resolution is quite strong when you're working with small molecules, but it's extremely poor for big molecules. So when you're working with small molecules, one of the things that will stand out is you will be able to obtain what is called the isotopic distribution of the particular sample of interest. So when we're working with small molecules, it's very important that in order for you to have a positive identification, you have to match not just the mass by charge, but also the isotopic distribution. All right, So I'm going to explain to you later on what exactly does it mean to have an isotopic distribution. But it's very important because this information, particularly the peak separation between the isotopes of a given species, will help you to determine the charge of the ion. And in terms of sensitivity, whether you're collecting data for small molecules or for big molecules, mass spectrometry is quite sensitive. With this instrument, because of the repeated use, I would say that our sensitivity is about 1 ppm. Again, small, big molecule, doesn't matter. Now, when it comes to the limits of the actual instrument, the MALDI instrument typically can't collect data for molecules that are beyond 200 kilodaltons. And then when it comes to the lower end limit, well, the lower end limit is really defined by the matrix they use, because the matrix is also a molecule and it will have its corresponding mass spectrum. And the matrix will be something that is quite abundant in the mixture with your sample. And so you're going to have a high background due to the matrix, especially at the lower end of the mass spectrum. So that's going to be essentially what defines the limits of what you will be able to detect. All right, so I want to give you a little bit of a perspective of what's inside the instrument. So when you actually go to this particular mass MALDI TOF, it actually stands up tall, whereas the MALDI TOF that's actually positioned adjacent to it is positioned in a manner that's horizontal. So this is more of the schematic that I'm used to, where it's actually tall. And so essentially what you have is the following, where at what will be the position of maybe our hips level will be where you would put the sample plate, and that is essentially where you'll have your source. So your plate goes into the source, you will shine the laser, and then using a series of mirrors to orient the laser that's going to shine onto the samples, and that's going to trigger the ionization process. So the ions will fly through the scheme. It will go into the tube, which is going to allow for that time of flight. And then there are going to be detectors, one up here, one down here, that are going to enable the detection of the samples. And so I'm going to talk a little bit about how the path of the particular samples of the ions will differ depending on the mode of collection. All right, so let's talk about the linear mode. Well, the linear mode is what you use if you're working with big molecules. Remember, big molecules, anything greater than 10 kilodalton. So essentially what's going to happen is that your sample, which will get ionized at the source, will travel through the time of flight, and then is going to get directed to a detector that's actually at the very top of the instrument. So that detector is the linear detector. So in terms of the flight path, that is an effective path of 1.5 meters. And so here's just a summary of this information. Linear acquisition mode is for the big molecules. Essentially, your ions are accelerated into the field free drift region, the time of flight. The ion optics steer and focus the ion beams toward the linear detector. All right, so now if you're working with small molecules, you're going to use the reflector mode. Okay, so very important to distinguish between the two. Linear mode, big molecules. Reflector mode, small molecule. All right, so what's the difference? Well, the difference is the path that these particular ions will travel. Well, we already said that smaller things are going to travel faster. And so essentially, these ions will go through the same path, okay, and it's going to go through the time of flight too. And it's going to get reflected by a mirror that's up here. It's actually not going to be detected by the detector that's up here. So that mirror that deflects the ions will orient it to another detector, which is positioned down here, which is the reflector detector. So those ions are going to travel an effective path of 3 meters. All right. So here's just a summary of what I just said to you, that when we're detecting things that are small molecules, you're going to run it in the reflector mode. And so essentially it's going to be oriented to the reflector detector, a distance of 3 meters these ions will travel. So I have a video here that we're going to look at that basically shows you the inner workings of how these ions are generated and move through the inside of the instrument. So I'm going to exit out of this presentation because I want us to see the videos.
The MALDI TOF process is a two-phase procedure. Initially, the samples are fixed in a crystalline matrix. In the initial ionization step, they're bombarded by a laser. The sample molecules vaporize into the vacuum while being ionized at the same time. High voltage is then applied to accelerate the charged particles. The second step is the time-of-flight mass spectrometry phase. In the linear mode, particles will impinge upon the linear detector within a few nanoseconds after ionization. Higher mass molecules will arrive later than lighter ones. Flight time measurements make it possible to determine molecular masses directly. Each peak in the spectrum corresponds to the specific mass of the particle along the time axis, starting with the ionization moment. In the reflector mode, the particles are diverted so that they fly towards a second detector. In addition to extending the flight distance, the reflector also focuses the masses. The combination of these two effects makes for higher resolution than in the linear node.
All right, so that gives you a perspective of the inner workings of data collection. All right, so the next thing I want to talk to you is there's another mode of experimentation that one could do. And so this is a mode that's called the MS-MS mode. All right, so what does that actually mean? Why is there two MSs? Well, that's because this is a fragmentation mass spectrometry. So what I was talking about before, reflector mode, linear mode, with regards to small molecules and big molecules, was the detection of those ions as they are, without any fragmentation. But here, you are intentionally trying to fragment your sample. What I mean by fragment, you're breaking it apart. And so there are different ways that you can do this. Is by a collision-induced dissociation. You can use just pressurized air. You can use some sort of gas that's basically an inert gas to break up the molecule of interest. So here I'm going to show you a perspective of this. So this is why you have what is called the MALDI TOF, because you're going to collect the time of flight of the original molecule in the ion form. And then the second time of flight is the collection of data of the fragments of that molecule. So over here, what we have is this molecule here, a small molecule. And so the full molecule is represented by the number 1. And so up here is the mass spectrum of that molecule, which I'm going to refer to as the parent ion. So this is the data for the parent ion. All right. So then when you apply the collision-induced dissociation, what you're going to do is break up this molecule. So the depiction here is imagining breaking up this molecule into different pieces. So there's a break between this carbon-nitrogen bond, leaving this portion of the molecule. That's this peak here, this fragment number 2. Then if you break here between this carbon nitrogen, you're left with this molecule here. That's this species here. If you break here, you have then the fragment number 4, which is this one here. All right. So then the idea for this is if you're working with an unknown and you're trying to make sense of what exactly this unknown, fragmentation can allow you to do this because it gives you the different pieces that when you add them up will give you the whole mass. And so these different pieces are like pieces of a puzzle that you can put together. As I've mentioned to some people who have worked with mass spectrometry, that sometimes you do have to complement this data with, let's say, proton NMR. And all of you in the PR Climb program have had the proton NMR training. So you can get a perspective of how you can couple some of this information with that type of technique in order to identify the molecule of interest. All right, so within the instrument itself, what's happening? Well, essentially what we have is the ion source where we detect the parent ion, which is going to go through the mass analyzer 1. Then that undergoes a collision within the collision cell that's going to break up part of the parent ion to form the fragment, the daughter ions. Those are going to go through the mass analyzer 2. And all this data is detected by the detector, and you get the output of the parent ions and also of the daughter ions. All right, so as you can imagine, you're going to be essentially making something that's small even smaller. So in terms of the schematic, this would be something akin to the detection of small molecules in the reflector mode, because you're basically fragmenting things into smaller sizes. So you're going to collect this in the reflector mode, but doing an MS-MS experiment. Essentially, your ions are going to travel through the same route that you would have without doing fragmentation for the reflector mode. So here's just a summary of what I just said. Essentially, that you're going to direct your parent ions into the source, into the mass analyzer, fragment those ions, create daughter ions, and then those again, all is going to get directed to the reflector detector at the end. All right, so here I have another video that's going to give you a better perspective of this. So let me go ahead and project this video.
Worker MALDI TOF process. MALDI TOF analysis provides additional structural information for target molecules. As MALDI TOF is a two-phase process. Fragmentation can occur by application of higher laser energies, known as LID, laser-induced dissociation, or a background gas can be introduced to promote ion collisions. This process is known as collision-induced dissociation, or CID. Samples are co-crystallized with a suitable matrix on a sample carrier. The samples are vaporized by the laser into a vacuum while being ionized at the same time. During this process, the sample molecules can become excited. The now charged and excited particles are accelerated through the application of a high voltage, and fragmentation can occur as they travel through the flight tube. In this process, precursor ions and their respective fragments travel together at the same speed. Based on the expected time of flight of the precursor ions, specific ion packages may be individually selected, and all other ions blocked from continuing through the flight tube. The selected ions are then re-accelerated, with the precursor and fragment ions traveling at different speeds towards the reflector detector. The ions travel via the reflector towards the detector, and thus a TOF spectrum is recorded. The detection of the selected precursor ion and its fragments creates a TOF spectrum. Whether fragmentation occurs through the use of higher laser energies or a collision gas, the structural details derived from the MALDI TOF spectrum provide a deeper analytical insight of the targeted compound.
Okay, so before we move ahead, any quick questions, any doubts? All right, so we're going to go ahead and move ahead. So that gives you then the context of the theoretical aspects of this particular technique and what's going on in terms of the insides of the instrumentation. So the next thing I want to talk to you about, which we will have practice with, is the process of sample preparation. All right, so here there is a video, but I'm not going to actually show the video because basically what it's showing you, what are the supplies that you're going to need when you're preparing samples. So this is at a scale where you're going to be working with micropipettes. So you need to have your micropipettes, the yellow ones, which are typically from 2 to 200. You need to have corresponding tips for those types of micropipettes. You need to have certain types of solvents. So the typical solvents that you're going to work with are water and acetonitrile. My suggestion to you is to work with mass spectrometry grade water or acetonitrile. In the absence of those, then HPLC grade is also acceptable. You're also going to need the plate, some spatulas, something to label your samples, because if you're going to make a lot of samples, it's easy to lose track of, and epi tubes, right? So that's essentially what you're going to need. And here is just sort of the list of my recommendation of things to have. So your solvents, your chem wipes, pipettes and tips, epis, epi trays and markers, access to a weight balance and weighing supplies, access to a matrix of interest, and also your sample. All right, so in order for you to get good data, there are three really important things, and that is that the instrument is under good conditions. And so that's on me, the person who is facilitating this instrument, to make sure that it is in good shape. So prior to the start of the REU, there was a few technical glitches with the instrument. I made sure that they were resolved, and so the instrument is in good shape. The next thing is to assure that you're using the correct set of methods to run your data. So that can consist of as many as three methods. Acquisition, which is what mode you're going to collect it, whether it's reflector or linear mode. Processing, which is the instrument's initial processing of the data to help in the analysis. And then if you're going to collect, let's say time of flight, or MSMS experiments, then you may also need to use interpretation methods. In what you're going to learn hands-on, we're going to focus specifically on acquisition and processing method, right? So the choice of method as it's appropriate for the samples that you're going to run. And then very important is the process of prepping your sample. This is not trivial, which is why I kept repeating to let me know what samples you want so I can guide you on this prep, because it's not something that's trivial. All right, so here's just the workflow of prepping your actual sample. So depending on the sample, you need to select a matrix. Once you select your matrix, you have to prepare your matrix solution. Then you prepare your sample solution, okay? You prepare these two solutions separately, your matrix solution and your sample solution. Then you mix equal volume, your sample solution and your matrix solution. You take that mixture, you plate it onto the sample plate, and you're gonna let that dry. So essentially you're drying it so that it crystallizes. So this is basically the workflow that you're gonna follow in order to prepare your sample. All right, so here is a table of some very well-established matrices that have been defined for certain types of samples. So what I'm gonna guide you through, particularly for your hands-on workshop, is the use of a matrix for small molecules that I have seen to be able to be useful for a number of types of samples. So initially, when MALDI mass spectrometry was designed, it was designed for something that would be more applicable to biochemistry. But more and more people have seen that you can actually expand the use of the technique and the selection of matrices to see many different types of samples. So I've been able, for instance, I'm a bioinorganic chemist, I work with metal compounds. I've been able to adapt some of these things to be able to detect my own types of samples. So this is a technique that's quite amendable to the samples, but it's very important that you know the properties of samples to see what matrix will be appropriate. So again, what's listed here as things that are more applicable for more biochemical samples, but certainly you will see that if you come across the literature, there are many different types of matrices that can be used for different types of samples. So let's say that you're working with peptides, which at least as depicted here would fall into the category of small molecules, less than 10 kilodalton. So then you would use this matrix, alpha cyano 4-hydroxycinnamic acid, or abbreviated as CHCA. Now, if you're going to work with proteins, so again, these are things greater than 10 kilodalton, then the recommended matrix would be the cinnapic acid. And so the rest of this list are some, again, well-established matrices. I haven't necessarily used them, or at least not to the extent that I've used the first two matrices, but again, these are quite well-established. All right, so what I'm going to guide you is a bit of the context of how do you go about preparing the matrix solution, but also, because this is a technique that involves crystallization, how to be familiar with the crystallization of your matrices. So here we're going to work with the, I'm going to abbreviate as cinnamic acid, although the full name is as written there. So this is applicable for small molecule peptides. I've been able to use it for a number of different types of small molecules myself. So what you're going to do is you're going to prepare your matrix solution in the MALDI solvent. In the MALDI solvent, the typical MALDI solvent is a 50% acetonitrile, a mixture with water that contains 0.1% trifluoroacetic acid. So the reason for the mixture of acetonitrile and the water is to try to have that nice balance of polarity so you can try to solubilize a number of different things. I will note that not everything, and you obviously, many of you work with things that are not water soluble at all, will go into these solvents. But that doesn't limit you being able to use this technique. I can show you different ways that I've been able to go around this issue in order to be able to see many different types of samples that are not soluble in water, and even if they're not soluble in acetonitrile. Now, you may wonder why the trifluoroacetic acid. The reason for this is because it provides a source of protons, and protons are one of the major adducts that are formed with your samples to give you charged ions, right? So that's a really important part of the use of TFA. So the recommendation is that with this multi-solvent, right, the 50% acetonitrile with the 0.1% trifluoroacetic acid, that you're going to prepare your matrix at a concentration of 5 milligrams per milliliter in this MALDI solvent. All right, now if you're going to work with cinnapic acid, and that's applicable for proteins, right? Here, you're going to use the MALDI solvent, but you're going to make your matrix at a concentration of 10 milligrams per milliliter. I will note that these two matrices do not immediately go into the solvent. You will need to do some amount of vortexing in order to basically induce the process of those samples, of those matrices going into solution. All right, so again, this is a process of crystallization, so be familiar with what is the typical crystallization pattern of your matrices. So to the left, we have this cartoon visual of what cinnamic acid looks like, and it does look like this, these type of spherical shapes that appear on the plate itself. If you see these type of crystals, and they tend to have a yellow color to it, then you know that the matrix is in good condition and that you actually prepared your sample really well. On the right is the representation of the crystallization of cinnapinic acid, and it definitely has a different crystallization, and so you see something that looks like this. Again, the same criteria. You see that, you know that you did a good job in terms of the preparation of your matrix. All right, so now what we're looking at here is a visual of the sample plate. So this to the right is what a typical plate will look like, and beneath the plate is an insert. So this insert is what's used in order to put your plate into the instrument. And it turns out that the insert and the plate are magnetic, and so they actually will be basically locked into place by the magnetic properties. All right, so each of those little wells that you see here is those wells, and so this particular plate contains 384 sample wells. So that means that you can have as many as 384 samples. I will note that when I do MALDI experiments, I tend to be pretty repetitive about the prep of my samples. What I mean by that is that I normally measure each sample more than once, and I also measure my MALDI matrix by itself, including the solvent that I use to make my samples, because I want to make sure that what I'm detecting in my sample is truly of the sample and not in my matrix or in my solvent. And that's going to be very important. And so everything I measure at least twice. Sometimes I I have 3 different preps of it, just because I want to be certain that I have reproducibility in what I'm detecting. All right, so what I'm going to show you here is a video for the process of properly cleaning your plates. So many of these plates have been used a lot, so you will see that they have, been worn down a bit over time. You'll see some scratches and stuff like that. The key thing is to just avoid, if there's a plate that's been used a lot, to avoid sections of the plate that have been damaged over time, because to some extent, some of these solutions that are made will damage the surface of the plate. So I'm going to show you the protocol for how to basically maintain the plates in good condition.
In order to clean the MALDI plate, you will need 2 basic solvents, water and ethanol. Please make sure that the water quality is distilled water. The first thing you'll do, as you will see, is wash the plate with some water and use a Kim wipe to rub down the surface. Next, you will use some ethanol and you will wash the surface again with a chem wipe. And then once again, wash with some water. It is a very good practice to clean the MALDI plate soon after use unless you want to preserve a sample.
Let's close that down. All right, so there's a few extra things I want to note to you about cleaning the plate itself. So typically I will use water and ethanol for the process of cleaning the plate. You can substitute the ethanol with some water, with some methanol or isopropanol. But you know, if you have ethanol, that's one that I would suggest to use. So let's imagine that you prepared a sample in a solvent. And as I mentioned to you, you're not limited by the solvents that I mentioned to you before. If you use a solvent that's not miscible with water or ethanol, then my suggestion to you is to use that solvent as part of this cycle of cleaning the plate after you have used and collected your data. So I would indicate this order, where you would wash the plate with water, then with ethanol, then the sample solvent that you use to make sure that all the samples removed from the plate, and then go back and wash with water to ensure that everything is off the plate. Okay, so that will be the final touch that you do. All right, so the next thing is how to go about preparing your matrix solution. And it's going to be important that you prepare the this carefully so that you have it in order to the MALDI solvent in order to prepare the matrix, but also to be able to possibly prepare the sample if the sample can actually go into the MALDI solvent. So here's a video that was prepared for this.
For mass spectrometry experiments, mass spec grade solvents are important. You will need acetonitrile and water. The typical MALDI TOF solvent is an equal mixture of water and acetonitrile. I usually mix 1 milliliter of acetonitrile with 1 milliliter of water. In addition, I add in TFA. It is an acid that helps to acidify your samples in order to see proton adducts. What I do is to add 2 microliters of the TFA into my mixture in order to have a final of 0.1% TFA. Now I'm ready to weigh out the matrix. Because I'm going to collect a MALDI of a small molecule, I will use cinnamic acid as my matrix. What I like to do is use an epi in order to weigh out a small amount of the matrix. In this case, I am aiming for a matrix solution that is 5 mg per milliliter. I take off my gloves, and you should do this only if you feel comfortable doing so. I take them off because they often create electrostatic attraction, which will cause for the powder to disperse all over the surface. And especially when we're working with a precious amount of sample, that is not an ideal situation. So I weigh out the powder directly into the epi. Again, I'm aiming for a solution that is 5 milligrams per milliliter. And so I determine the volume that I will add based on the mass that I weigh out. I then add the corresponding volume of the matrix solvent in order to obtain a final concentration of 5 milligrams of the matrix in 1 milliliter volume of the solvent. To remind you, the solvent consists of 50% water, 50% acetonitrile, and 0.1% of TFA. I often have to vortex the solution because it's not readily soluble.
All right, so when it comes to then preparing the next set of solutions, it's very important to be aware of the type of things that can cause for contamination for low quality sample prep. And so there are a number of things to look out for. You may have some contamination that's coming from the matrix itself. We can give you some pointers to where, if you're going to buy matrix, where you should buy them from. So the matrix that we'll be using are ones that have been extensively used, and I know that there should not be a problem. So the next thing, as I mentioned to you, is the solvent. So again, as long as you follow the criteria of at least HPLC grade solvent, you should be okay in terms of the prep of the MALDI solvents themselves. So the next source of contamination may be the samples themselves, right? Because, you know, we were preparing samples not necessarily in solvents that are the highest grade. And so that's okay, as long as we know what ingredients we're putting into these solvents. And this is very important when you're considering that the technique is based on the measurement of ions. One of the things you definitely do not want to include or not include much of is external salts, because salts can definitely give you a very high signal as they are, you know, made of ions. So characteristics of contamination are the ring effect around the sample spot, clumping of the matrix, because remember, the matrix is supposed to crystallize. If you see clumping, there's something wrong with your prep. Or if your droplet spreads over the wide area, doesn't actually stick onto the surface. Maybe there's something wrong with the surface of the plate, causing for the sample to just not actually stay on. All right, so there are a number of things that you need to take in consideration, especially when you're working with biological samples, that can be used in the final samples, but other things that cannot be used. So things that are not interference, did not cause interferences. TFA, well, as you know, TFA is typically used in the MALDI solvent. Formic acid, again, is a source of protons. Beta mercaptoethanol, DTT, these are things that are used for reducing samples. Volatile organic solvents, if anything, I recommend you to use something that's volatile, something that can easily evaporate. The use of HCl, ammonium hydroxide, acetic acid, these are perfectly fine. Now, if you do have to work with a sample, let's say you have to work with a protein sample, and some proteins do not like to be without salt, then you might need some amount of buffer, okay? If you're going to use a buffer, they must, the use of it must be at a low concentration. So lower than 5 millimolar. Even 5 millimolar is pretty high. So if you're going to use a buffer, my suggestion to you is to use an ammonium-based buffer, so ammonium salt of a volatile buffer. But please avoid the following. Avoid glycerol. Glycerol is typically used, especially in the storage of proteins, avoid it. Sodium azide, DMSO. That's why I emphasize that if anyone needs to bring samples made in DMSO or DMF, to do it at very high concentration, because we're going to have to dilute it. The instrument will simply not collect good data with DMSO present, nor will you be able to crystallize your sample in that. SDS, phosphate, sodium chloride, 2 molar urea, 2 molar guanidine. These are things you need to avoid. All right. But there are going to be occasions that you have a sample that you want to see in MALDI and it's pretty dirty. And that's not necessarily the, the end. You can certainly clean up your sample, and there are different ways in which you can do it. So a classical way is that if you have a pretty high concentration sample, you can do the method of dilution. That works well. That's why I suggest you make a sample of DMF or DMSO, then we're going to dilute it extensively so that we have, let's say, no more than 2% of these solvents in our background. You can also do what's called an on-plate washing, where I haven't personally done this, but supposedly it can work. where you crystallize your sample on the plate, and then you use some 1.1% TFA in water, and you pipette that up and down on the sample, and that's supposed to remove the contamination. My fear is that you might actually dissolve something that you're interested in. You can, apply your samples onto a column and use a type of chromatography. People might use cation exchange. Like for instance, you want to replace sodium with ammonium. Ammonium flies better in mass spec. Another thing is to use columns, but that are tip columns. For instance, today I was just showing a student in my lab how to use a zip tip. A zip tip is essentially a column that one can clean up samples by reverse phase chromatography. And so here I'm going to show you a picture where this is a zip tip, which looks like an ordinary tip that you would use for pipetting up samples from 0.5 to 10 microliters, but the column is right at the tip. And so you use that, and basically it binds hydrophobic things very well. Hydrophilic things do not bind to this. And so there's a way that you can clean up, let's say, peptides that would bind to this column, and you can elute it with acetonitrile. So here's a protocol. I'm not going to go through it because this is a standard protocol you can find online, or you can find it accompanied with the pack of tips that come from the company. But I provide it to you so that in your spare time, you can read this slide much more carefully. But the point is that there are ways to clean up sample if you need to run that sample with the MALDI, and you need to do so right away. All right, so that concludes the discussion of sample prep, all right? So now what we're gonna talk about is the brain work that you need to do, because again, don't just bring a sample and go to the instrument. You need to take the time to think about your sample and what to expect to see. So predicting sample ions by generating theoretical mass spectra is critical to effectively use your time at the instrument, and in that instrument time to finish your analysis. I will tell my student, last week, I had a student who was about to leave the instrument telling me, oh, it didn't work. And I was like, no, you got to stay there and figure out why did it not work. And it didn't work because the sample was a smaller size than the mass range that she was using. So it's very important to be conscious of what mass do you expect to see. Don't just use the standard parameters of the instrument, because you're going to get nonsense, and we don't want to waste time with nonsense. All right, so the whole process of preparing for data collection. So before collecting data, it's very important to make a list of possible ions that may be present in your sample. Okay, so to do so, we have to think about the composition of our sample, but very importantly, what's going to make it charged, either positive or negative in terms of charge. So the data that you collect are mass spectra for compounds in ion mode, ion form, and results are reported in the unit of mass by charge. Keep that in mind. That's actually very important. Another very important thing is determine what sample ions you expect to observe in positive or negative ion mode. There are some species that you can detect better in positive mode, and some that you can detect better in negative ion mode. And so let's say that you don't see anything in one mode, don't give up. Maybe just switch over to the other mode, and you might be surprised, you might see what you're interested in. Another really important thing is to note, when it comes to MALDI TOF, you are typically going to see things that are +1 or -1 when it comes to small molecules, okay? +1 charge, positive ion mode, -1 charge, negative ion mode. But when you're working with large molecules, you may be able to see also not just the +1 and the -1, you're certainly going to see them, but you may also be able to see +2 and -2 ions, okay? So that's very important. Small molecules, +1 charge, positive mode, -1 charge, negative mode. Big molecules, positive mode, you will see +1, +2, and the rare occasion +3, but typically +1, +2, and negative mode, -1 or -2. Another really important thing is the signal sensitivity. And it turns out that for the negative ion linear mode, remember linear mode is for the big molecules, it turns out that the signal sensitivity is much inferior for the negative ion mode than it is for the positive ion linear mode. So my suggestion is to stick with the positive ion linear mode. And then when collecting the mass spectra of small molecules, you should be able to obtain excellent mass resolution and observe the isotopic distribution of the ions present in your sample. Again, this is for small molecules. So we're getting back to that concept of isotopic distribution, which I have not yet defined, and we're going to do so in a moment. All right, so I'm going to do so by looking at a particular example, and I'm choosing a titanium-containing compound, not because I work with titanium, but because this is actually a really good example of isotopic distribution. So when you are referring to the element titanium, the isotopes, there are several titanium isotopes, but there are 5 stable titanium isotopes, and those 5 stable and abundant titanium isotopes compose what we know as the titanium that you can bind to different things, or you can molecules with. So here in this table is a list of the 5 stable titanium isotopes and their corresponding abundance. And so you have 46 titanium, an abundance of 8.3, 47 titanium, abundance of 7.4, 48 titanium, the highest abundance of 74%, 49 titanium, 5.4, 50 titanium, 5.2. All right, so this is the reason why the atomic weight of titanium is 47.867, because that number is dominated by the abundance of titanium 48. That is the highest one. That's why you get that average number. So what I mean by isotopic distribution is that when you detect your species of interest, your ion of interest, you're going to see the isotopic contribution from all of the atoms that compose that molecule. So a molecule that has titanium will be, you will see the evidence of these 5 different isotopes. So let's look at a particular example. Here we have a molecule. This is titanium with 3 citrate molecules coordinated to the titanium center. So you have these 3 different citrate molecules that are coordinated in this fashion that's referred to as bidentate coordination. And so if you were to look at the charge, remember, again, you have to think about the charge. This coordination will give you an overall charge of 2-. So this is something that's dianionic, okay? So we're looking at something that's going to be a small molecule that we're going to detect by MALDI using the reflector mode. But remember, reflector mode, small molecules, we see things that are either +1 or -1. We wouldn't see -2. So the question is, what type of adducts can we predict to form that we might be able to detect? All right, so let's write up this composition here, right, of the diion of titanium citrate. So I just basically wrote it in this elemental form. And then a possibility is that because of the TFA in your MALDI solvent, right, that the protons will interact with your sample of interest, with your species of interest, and it will form a proton adduct. You will need 3 of these protons in order to form an adduct that has a +1 charge. That +1 charge can be detected by the positive ion mode. And so that +1 adduct has a monotope weight of 621 mass by charge. So there's a program that if you have a PC, you should be able to download, which is called, and it's download for free, IsoPro 3. I use this a lot, especially for data analysis, and a number of students use this program. And so it predicts the mass spectrum for you. So again, this is the work that I suggest you do prior to doing your actual data collection, because you can see what you're supposed to see. So you're supposed to see a mass spectrum that looks like this, which is the titanium citrate, right? Where you have this isotopic distribution. Now you see you have more than 5, because remember, your isotopes are coming from all of the atoms, the titanium, the carbon, the hydrogen, the oxygen, and these have different isotopes, right, abundances. But you have a pattern that's indicative of at least the 5 titanium isotopes in there. All right, so what does that mean? Well, 619, 620, 621, 620, these are all the same species. It's just the different isotopes that are part of the species. But there's also something really important, and it's the separation between these isotopes. What does the separation mean? Well, remember, your axis here is of mass by charge. So it turns out that the separation is the measure of the charge of that species. So a separation between the peaks of 1 means that you have a charge of 1. If you're in positive mode, that charge will be +1. If you're in negative mode, that charge will be -1. All right, well, let's continue on that theme. If you have a separation that's 0.5 based on mass by charge, that means that the charge state of your species is +2. If that difference is 0.33 based on mass by charge, that means that your charge state is +3. Okay, so that's how it works. It's very mathematical and is a very nice way to confirm that you have a certain charge state, and based on the isotopic distribution and the base peak, right, of that species, you can identify whether or not you have what you're interested in looking at. All right, but the proton is not the only adduct that can form. Another adduct that can form is the sodium adduct. All right, and so maybe you don't prepare your sample with sodium in it, right? Because I told you already, don't use any sodium salt if possible. Sometimes your compounds already have sodium as part of its composition. Another thing is that the instrument tends to have some amount of residual sodium ions at the source, because people will use sodium in samples, even though I tell them, please don't use it. You know how much people really listen. So you're going to have some sodium in your source, and that can be something that can form an adduct. And so here I have a representation of the titanium tricitrate with 3 sodiums forming this adduct, this +1. Okay? And that +1 can be detected by the positive ion mode. And then you see the corresponding mass spectrum, theoretical mass spectrum, and the corresponding isotopic distribution. And again, the separation of the peaks is a measure of the charge. Another thing that you can have even mixed ion adducts, where let's say you have a mixture of proton and sodium adducts. That can happen. And here's an example where you have this theoretical mass spectrum that corresponds to the mixed ion adducts. Typically, you may see just proton adducts or the sodium adduct. It's rare to see this mixed ion, but if you do, then just keep that in mind of the possibility. All right, but in addition to seeing things in positive ion mode, you can also collect things in negative ion mode. So if we're thinking back to the original titanium tricitrate, that was dianionic. And so to look at something in the reflector mode, negative ion, you need to be able to see it in its -1 charge form. So for something that's dianionic, -2 in charge, it would only require a single proton or maybe even a single sodium in order to form an adduct that is negative charge. So what we're seeing here is the theoretical mass spectrum for the species here, this titanium tricitrate that is anionic, a charge of -1. And again, the separation of the peaks is an indicator of the charge. So separation of 1 means that you have something that is -1 in charge. All right, so additional things to be mindful of. When examining a sample for the first time, it is good to prepare your sample at 2 to 3 different concentrations. A good rule of thumb is 10, 100, and 1,000 micromolar. Although 1,000 micromolar, I normally leave that for like samples that are in solvents that are not mass spec compatible so that I can dilute. My typical recommendation for sure is 10 and 100 micromolar, even though 100 micromolar is quite high in concentration, right? But this is good to have because there is this misconception that in order to see things extremely well by mass spectrometry, you need really high concentration. And actually that's incorrect, because by having such a high concentration, you will saturate the signal, and that's going to lead to really poor quality data. So typically, as long as you have very good sample prep, you want to aim for the lower end of the concentration region. Remember, you can go down to 1 ppm. That's like that's probably like low micromolar, high nanomole for certain species. Another thing is that, what if you don't detect the sample of interest? Well, you can try other matrices. Look in the literature and see what they recommend. And for some people, like for myself, I may want to see things in a particular pH. And so when you're trying to look at something at a particular pH, then you're going to need to use buffers. But I already told you, avoid buffers as much as possible. So if I'm going to do an experiment like this, that's pH dependent, my option is to work with buffers that are ammonium based, and that I include them in my sample at a very low concentration, so that I don't perturb the quality of the mass spectrum that I collect. All right, So let's imagine that we're collecting data on a real sample. And so you're going to do this in person tomorrow, okay? But I want to give you the preview so that you already start to think about what's the thinking behind this preparation of sample and the collection. So let's work with another titanium compound. I'm looking at a different type of compound where we have this this chelator that's bound to the titanium. So tridentate means that it coordinates at 3 different atoms. 2 of them saturate the titanium. This molecule is a neutral compound. So neutral compound will not be something that you would detect by the MALDI. So we have to transform this into something that's an addict that's either positive mode or negative mode, right? So the first thing we do is we do the thinking behind the preparation of the sample. We have a neutral species. So what we're going to do is we're going to create an addict that has a proton. Okay, so this is going to be my little list of ions that I'm going to think about before I collect the data. I predict what I'm going to see. So I create this, and so I'm going to go through you the exercise of preparing my sample, going to the instrument, and trying to process this information. All right, so look at these videos.
It is time to prepare the sample solutions. I previously prepared a stock solution of a small titanium compound that comes from my laboratory. It is important that when you prepare your final set of solutions, that you select a solvent that is compatible with the solvent used to make the matrix solutions. In this case, I diluted my stock titanium compound to 2 concentrations, 200 micromolar and 20 micromolar. I did this to have 2 different concentrations with which to be able to analyze my sample. I then prepare the final set of solutions by combining the matrix solutions with the small compound solutions. To do this, what I do is I pipette 5 microliters of the matrix solutions into 2 different epis. Into these epis, I will pipette 5 microliters of the 200 micromolar compound, and in the other epi, 5 microliters of the 20 micromolar compound. In effect, I dilute both samples by half. So I will have 10 micromolar samples and 100 micromolar sample. In total, I will have 10 microliters each, which will be plenty of sample to be able to work with. It is always a good practice to label your sample epis, especially when you have many samples to keep track of. I will next spot the sample solutions onto the MALDI plate. In addition, I will also spot the matrix solution alone, which will serve as a control. The matrix solution will show us how the matrix itself crystallizes, and it serves as a good indicator of how good our sample solutions are, because the sample solutions should also produce a crystallization comparable to that of the matrix solution by itself. If you see a spot that looks extremely different, let's say crystallizes or does not, or produces a very dirty spot, you know that your sample was not well made. Each well of the MALDI plate can hold a minimum of 0.5 microliters, but I deliver a total of 1 microliter in order to cover the entire surface of the well. For each sample, I spot 3 different wells. So there will be 3 wells of matrix, 3 wells per concentration of small molecule. One can take another approach if the sample does not dissolve in a solvent compatible with the solvent used to create the matrix solution. What I do then is to spot the MALDI well with the matrix and let those spots crystallize. And after they crystallize, I then spot 1 microliter of the sample solution on top, so that now that sample will crystallize on top of the matrix.
All right, so the next thing we're going to do is we're going to look at how, once we have our sample already spot onto a plate, imagine us going into that, the MSRC, which everyone's going to have this experience tomorrow, and we're going to look at the process of calibrating. And you're all going to see this process live. But again, very important to get this perspective before you do.
This is the ABSIX 4800 MALDI TOF located in the Molecular Science Research Center. The MALDI TOF is always on, as is the computer. You first click on the software 4000 Series Explorer, which is located on the desktop. There you will see the program itself, and what we'll do is first open up a file which is called a spot set. What you should do next is to find your lab's folder. In this case, I will look for the Tinoco lab folder. Next, I will give a name to my particular spot set. In this particular case, what I will do is give it a name that corresponds to the date, and what we'll do first is to do a calibration, so I'll call this cal, the date and the abbreviation cal. I will copy this name, hit create, and then I will paste the same name here so that I use it to call my plate name the same. Here I have to select the type of plate, and in this case we're using a plate that contains 384 wells, so that is the option that I would click. There are 2 plates that are used to perform calibrations. CalMix 3 is used for big molecules, and CalMix 5 for small molecules. CalMix 5 is what we will use for our sample. When we open up a plate for the first time, it will be located in a plastic sleeve. We remove that plate, and as you'll see, it is rectangular. There is one corner that is indented, and that's intentional, so that it can be placed aligned to that spot in the insert. The insert is magnetic, so the plate will be held in place, and you tap on each side to make sure that the plate is locked in nicely. Next, we will apply an air gust to remove any particles on the plate. We will take the plate to the instrument. We will align the plate according to the indented side, and there's a picture that you will see right in the inset. You'll line it carefully, and then you will let the door close. In the software, you will click on Plate and Load Plate. Then you will search for the spot set that you created for this particular plate, which was, if you recall, the date and the abbreviation cal. Click on that and then hit select. What this will do is it will lower pressure, essentially applying a vacuum in order to load the plate. Once the pressure reaches a low enough point, the instrument will grab onto the plate and insert it inside. And then a vacuum will be applied. The pressure icon will disappear. Now you'll be able to see the plate because the camera can actually visualize each of the wells. And there's a drop-down menu that can help you to select which well you want to look at specifically. Because we are using a calibration plate, each of the wells is identical. We will now open up a method in acquisition method. In my folder, the Tinoco folder, we will search for a reflector method that collects in the positive ion mode, the MS reflector positive method. There are many windows that will open up corresponding to this method. Draw your attention to the mass range, 800 to 4000, that encompasses the mass range of the small molecules that are contained in the calibration plate. We will next open up another method called the processing method. Here, we're going to look for a method in the Tinoco folder with a name that is similar to the acquisition method. In this case, we're going to click on a reflector positive internal method. We choose an internal method because we're going to perform a calibration. Now we have both methods open. I will click on the acquisition method here, and now the processing method, so that you have a sense of where to find them on the screen. In the processing method, I'm clicking on the calibration icon, and these are the parameters used to collect the data. The small molecules that are used in this particular plate are peptides that are of the masses between 800 and 4,000. I click on this bolt icon, which will turn on the laser. When the laser is on, you will see that it becomes green and say laser on. Next, we will collect data on one of the wells, and remember, all the wells have the same material in them. To do so, especially for calibration, click on calibration as the type. Now we'll click on this icon here, and here we collect the data, and the data appears within seconds. So you should see several peaks that correspond to the different peptides. We will zoom in on one of them, and it is the peptide that has a mass of 904.46, and you see the isotopic distribution, a difference of +1. We will save the data, so you click on the save icon, and then return to the acquisition method. Within this method, click on the operating mode, and then click on update default calibration, because we will collect all the data in a default calibration method.
All right, so what we're going to talk about, or we're going to see now, is the process of actually collecting data. So let's go ahead.
We are ready to eject the calibration plate. Click on the plate icon and then eject plate. Once the pressure is released, the instrument will eject the plate, as you will see. We will remove the calibration plate from the insert. Behind, you will see a space that you can use to push your finger and remove the plate. And then we will place our sample plate onto the insert, as so. We will create a spot set for our sample in a manner analogous to how we created the spot set for the calibration plate. Once our sample plate is inside the MALDI TOF instrument, we will need to open up another method. The acquisitions method will remain the same, but the processing method will change. We will have to select a reflector positive method that is labeled default, because we need to use a default calibration in order to calibrate the sample while we collect the data. We now have to activate the default method. We click on this icon to then set the method as active. We then have to go into the acquisition method and adjust the mass range. We will choose a mass range from 400 to 1000, because that is the mass range that is appropriate for our small molecule. And we also adjust the focus mass to a value that is within the mass range selected. We will next collect data on A1, and if you recall, A1 contains only the matrix because it is important to see what is in the background so that we can identify peaks that correspond to the matrix in our actual sample data set. I noticed that our laser intensity was high, so I decided to lower it to a more moderate amount. It was originally 5,000, I've lowered it to 4,000. When I do so, I have to recollect the data. Make sure to save the matrix-only sample. Next, we will collect data from the well A4. If you recall, A4 contains 100 micromolar sample. When we collect the data, we will see that there are two new ion peaks, and they appear higher than the intensity of a peak that appeared in the matrix-only sample. We will zoom in onto these two ion peaks. There is a peak at 791, which we believe is a proton adduct of our desired compound, and 813, which we believe is the sodium adduct. We will next collect data from well A7, which is the lower concentration, 10 micromolar. Here again, we see the two ion peaks, but they are lower intensity, but still the resolution is quite good. Again, remember to save your data set. Finally, we will collect data for the sample that was prepared by first crystallizing the MALDI matrix, and then on top of it, crystallizing our sample. Here we see the two ion peaks, but the quality of the ions is simply not as good. This is not always the case. There are many examples where this method works quite nicely, but in this particular example, it did not work very well at all. Click on the plate icon. We will now convert the data set to be able to analyze it in a plotting software. You right-click on the file name and you click on the actual data set. I'm actually zooming in on the data set into the region of interest. And then I right-click and click on the copy XY data. I then open up WordPad and insert the data that I copied here. Then I save this data set into my folder. I normally will put it into a folder that corresponds to the date in which the data was collected. This is useful in order to be able to track the files collected and record the date in my laboratory notebook. It is a very good practice. It is important to save the sample dataset and the matrix-only dataset. Now, transfer the dataset to your email.
Okay, so it's very important, that last point there, that when you collect your data, to send the data by email only. We don't put any memory keys into the instrument. The instrument's quite old, especially the computer, and so send everything by email. So in your actual PowerPoint presentation, you will see that there is a video that talks about how to calibrate the instrument in linear mode. We're actually going to skip that particular video because it's basically the same concept as calibrating the instrument in its reflector mode. The last thing that we're going to focus on is analyzing the data that we've collected. So we already collected the data. We would have transferred it by email, and then now you're sitting at your computer and you can use a simple software like Excel to look at the data and to be able to plot it in a manner that is publishable. So we're going to focus on that now.
I will show you a simple but effective way to analyze your data. First, open up your sample data set in Excel. Then you will use a software that is available for free online called IsoPro 3.1. Here, click on Edit, Formula, and type in the formula. So here I type in the formula of the small titanium compound. Click on OK. This yields a theoretical mass spectrum of a proton atom of the compound of interest. I click on Edit, copy the XY points, and I take that information and I paste it into the Excel file. Now I have the data in the Excel file for both the experimental and the theoretical mass spectra. I will first plot the data for the experimental. I'll click on Insert, Chart, Scatter, and the line feature. Then I will zoom into the data set in the x-axis, and I'm actually zooming into a mass region that corresponds to the proton adduct of my sample of interest. I will next identify the intensity of the peak of highest intensity, and I'm going to use this number in order to normalize my data. So I will create another column in which I will write an equation taking the intensity from the y-axis and dividing by the maximum intensity that I observed in the plot. You can actually look through the columns to find what that maximum intensity is, and that is what I did. I multiply this fraction by the factor 60. So 60 will now become the highest intensity, and you will see in a moment why I did this. The data that was obtained from the theoretical mass spectra that was generated from isoprobe was already normalized to 100. What that means is that the highest peak will be 100 for the theoretical mass spectra. So I'm actually going to insert this data into the plot. I will click on Select Data, and I will add the series corresponding to the theoretical mass spectrum. For the Y values, I will click on the column of the experimental data set, and then for the X values, I will click on the column that corresponds to the X values of the theoretical data set. You can name the series name, and that's what I did here. I called it theory, something simple. And so essentially what I've done is I overlaid the theoretical mass spectra on top of the experimental mass spectra. And the next thing I'll do is to distinguish between the two data sets. The program has done this in part by giving a different coloration, the red for the theoretical and the blue for the experimental. I've changed the patterns such that there's a dashed lines for the theoretical and there's a blue line for blue filled in lines for the experimental. If you hope to publish this information, sometimes journals do not allow it for color, and if they do allow it, they may charge a fee. Now I'm just cleaning up the figure, removing extraneous lines and also removing chart title. I'm also going to add in axis titles. The x-axis will be labeled m by z, which means mass by charge. That's how you read the data. And the y-axis will be labeled relative intensity. As always, save your process data. It is a good idea to save it with a name that corresponds to the date of data collection so that it is easy to track and record the information in your laboratory notebook.
All right then. So that basically concludes the process of calibrating the instrument, collecting your data, and also analyzing data. It's actually something that's extremely quick, the process of collecting the data and sifting through it. But the key thing about maximizing the output of the success of your analysis is all the brain work to figure out what are the possible mass spectra that you're going to see. So before we conclude, do you have any questions, any doubts? Seems like everyone's doing really well. So what we're gonna do then is we're gonna take a quiz. Okay, so I'm gonna need everyone to get on their microphone because we need to answer this as a group. All right, so here's our quiz. So the thing is that we need to figure out what, for these different parameters, what corresponds to a small molecule and what corresponds to a big molecule. So I'm gonna see if there's any volunteers. What is the size for something that's considered to be a small molecule?
Less than 10 kilodaltons.
Less than 10 kilodalton. All right, that's Justin. All right then, somebody else, not Justin. What then defines something as being a big molecule size? Somebody else. You can call some names.
Greater than 10 kilodaltons.
Very nice, Kennedy. Good. All right. So then, what acquisition mode would we use if we wanted to collect something that is a small molecule?
It was like reflective.
Okay, yeah, reflector mode. Good.
Reflector.
Right. So someone who is not Kennedy and not Justin, what acquisition mode do you collect for something that is big molecule?
Linear?
Linear. That's correct, Juan. Good. So someone that's not Justin, Kennedy, or Juan, can you detect isotopic distribution for small molecules? Reflector mode. Yes or no?
Yes.
That's correct, Elizabeth. Thank you. But what about for big molecule, linear mode? Yes or no?
No.
Thank
It's
you,
hard to
John.
detect.
That's good. Very good. All right. Now, someone who's not any of those people, okay? Detection level. What's the detection level, the lower end that you can detect for small molecule at a ppm level? What's the level that you can detect?
1 ppm.
Thank you, Rolando. Okay. So someone who's not everyone who's answered, detection level for big molecule. I'm going to start asking if no one answers. Catherine, are you there?
I am here. I don't remember.
Okay. Try to cheat off of Rolando.
Okay, I will say though, Kennedy cheated off of me.
Okay. Well, then, cheat off of Rolando. What did he just say? I think it was Rolando.
He said 1,000.
No, he didn't say 1,000. Rolando, what did you say?
1 ppm.
What did you say? Say that again.
1 ppm.
Okay, Catherine, what's the answer?
1 ppm.
That's correct. Thank you. All right.
Okay.
All right. Someone who's not any of those people, what ion charge is likely to be observed for small molecules, reflector mode? Let's see, Christine.
I'm just gonna guess here, +1.
+1. That's good. But there's another charge you can detect in the reflector mode. What's the other charge?
Plus or minus
That's good.
-1 or yeah.
Yeah, plus or minus 1. That's good. Very nice. Okay. So someone who's not any of these people now for ion charge likely to be observed for big molecules. Okay, who else is left? Renee.
Plus or minus 2.
Oh, Bianca, good, good. Plus or minus 2. And what else? Renee.
Neutral molecules?
No, never neutral molecule, not with this technique. So Bianca said plus or minus 2, but there's another set that you can see in for big molecules linear mode. Who can help her? Anna, you there? You can help her.
Sorry, we're like both looking at the PowerPoint right now.
That's
Sorry,
good. That's the
not
way to
working.
do it. You got to cheat. You got to look back. Select the notes. That's why I give it to you guys. Yep,
Wait, if it's plus or minus 2, can I also detect plus or minus 1 or no?
exactly. Yes. Plus or minus 1 is the dominant one. And plus or minus 2, you can also detect in the linear mode. But the dominant one for both reflector and linear mode is plus or minus 1. All right, everyone. So all the peer client people seem to have passed. I hope everyone else passed too. So I'll peer client people and also some of the other people that I added to the schedule. I'll see you tomorrow in person to do this live. All right. Have a good night. Bye-bye.
Good night. You too.
Good night.
Thank you.
Thank you.